All right, so now it's 3 o'clock, so I think we'll go ahead and get started, and people can drop in over the next few minutes. So I would like to welcome everybody to this third and final round of Live from Behind the Walls this semester. We'll be back in September, of course. So before I hand you over to our host and moderator, Peter Gorm Larsen, and all of the great speakers, I just have a few things to take you through. First of all, this talk is being recorded and will be posted online afterwards. If you missed some of the previous events, you can watch the recordings at the bottom of the page where you signed up. So I would like to present the organizing team, Peter Gorm Larsen, who is the initiator behind this concept and a professor here at the Department of Electrical and Computer Engineering. And as I said, he will act as your host, moderator, and timekeeper today. And Hugo Macedo, who works as a research assistant here at the department. And my name is Lide, and I'm the community manager of Orbit Lab, which is also part of the department. If you feel like it, you're welcome to present yourselves in the chat. And to those of you who are less familiar with Orbit Lab, I can tell you that we're a tech and innovation hub and an open community for anyone with an interest in digital technologies, entrepreneurship. And as I said, we're part of the Department of Electrical and Computer Engineering here at Aarhus University. And if you want to know more, of course, you're welcome to contact me. So finally, we host a number of online these days online events, but hopefully soon physical events that everyone is welcome to attend. All our events are open. So we're currently planning events for the next semester, and we hope to be able to truly invite you in behind the walls in real life for future events and future live events and other events, of course. And if you want to keep an eye on our upcoming events, here's a list of the platforms where you can find information. So that's it from me. I will now hand over this virtual stage to you, Peter.
Thanks. I will just try to share my screen and have a presentation mode. Do you see that?
Yep.
Very good. Thanks for the introduction, Lide. I would like to kind of start by saying that at the Department of Engineering, we're divided into different sections. I am the head of section for software and computing systems, and these people are the people in the section who are involved with research activities. And you'll see there are some unknown places, meaning we have some open positions, or are going to have some more open positions in some cases, where we are missing a few more people to join us. And there are some people in the corner that I don't have the pictures of, so they are just listed like this with their names. But it's quite a large team of people who are involved in different research projects. And there's also quite a lot of projects with funding from different sites, and they have different leads from the section. And they go over different times. So you'll see quite a lot of projects started in 2020. So we have been rather successful in attracting grants there. The 13 projects that are currently ongoing have more than 100 million euros in total, not our budget, but the budget of the entire consortia. But in total, our budget is more than 10 million euros. And here it's listed in Danish kroner. So obviously you're going to hear about some results from some of these projects, but you're also going to hear about different student projects in here. Here's the program where I'm trying to set the context at the moment. And the first presentation by Jonas Rask is actually kind of an extension of the master thesis that he and Frederik Madsen was doing. And it's something related to Visual Studio Code, built on top of Visual Studio Code, for those of you who know this platform. Then afterwards, there's a presentation by Tomas Kulik. Essentially, this is 20 minutes cut down of 3 years' work of his PhD project with an industrial partner. After that, we have a presentation by my colleague Morten Opprud, and I don't have a photo of him, so I didn't bring it in here. It's also an Innovation Foundation project, and it's not from our section, but it doesn't matter. What we try to communicate here is research conducted by my people and the friends of the community. Actually, I can say that the next version, the one happening in September, was not going to be hosted by me, but hosted by Daniel Rytter, one of the other section heads at the department. But after Morten Opprud, we're going to have a presentation about some new work on design space exploration for co-simulations from a colleague of ours from Newcastle University, collaborating with some of my people as well. And following that, we will have Gill. Oh, I did have a photo of Morten. Sorry for that, Morten. Then I have a photo of Gill. It's a rather old photo, I should add, but he and two of his friends, Jakob and Jakob, were doing a bachelor thesis project with me last year, and they were doing a digital twin, or towards a digital twin for a desktop version of a large agricultural robot called Robotti. After that, we have another student project, which is about bio-inspired multimodal object recognition. I know absolutely nothing about this project, so I really look forward to hear about it. And then there's a presentation by one of the research assistants we have, which is Kristoffer, who have been working on something called the INTO-CPS application, which is on top of this co-simulation framework we are having. And at the end, I'll give a few closing remarks. But as you can see, it's quite a tight schedule. So what's important is that I would like to ask everybody to keep to time. If you see me turning on my camera before time, you will recognize that, well, maybe I should end soon. And then I'll ask everybody to mute their phones when they are not, or mute their mics when they are not supposed to speak. We don't have time for really asking questions. So what I would like you to do is that you kind of type in the questions you might have in the chat, and then the speaker will try to respond to you after he's done with his presentation. So this used to be quite a lively way of doing things, so please follow those principles as well. And then I think that's all I wanted to say for now, and I'll stop sharing my presentation. And then I think Jonas, you are actually first.
Yes, thank you. I will just start sharing.
So, and all of you, if you are not, when we are not kind of in common together, like now and at the end, please remove your video thing so we don't need to use the bandwidth on that. Thanks. Okay, Jonas, over to you.
Yeah, thank you. Okay, what just happened? There we go. Yes, so I will do this presentation that we have chosen to call an LSP extension for specification languages, Exemplified for VDM, which, as Peter mentioned, is an about a master project by myself and Frederick Madsen. So I will start with a short introduction, followed by talking about something called language-neutral protocols, and how these can be used for supporting specification languages. And finally, I'll talk about what we have made, which is this specification language server protocol, and this support for VDM in Visual Studio Code. So if we start simple, then when we're using IDEs, for instance, to write normal programming code, then we have this called language features or language smarts, which help us in our editing of code or debugging and something like this. So this could be syntax highlighting or syntax checking type checking or refactoring or things like this. And the same we see in an editor like Visual Studio Code. Normally the way to do this is that you have for each language, then in each IDE you have the support specifically for one IDE. So if you have Python here and you have Visual Studio, then you have one implementation up here, and for Vim you'll have some other implementation. And this leads to a lot of different things that you need to maintain if you want new features. And also, if you want multiple languages, this gives you problems, since it's a lot of work to for instance, support all programming languages in one editor. When Microsoft made this Visual Studio Code, they came up with this solution using this LSP protocol, where they divided the support into a server part, and then you have a generic client which knows nothing about the language itself. So what we see is that the language support is created in this server that has all the information about the language, and it can then be used for each client. And this allows you to carry it around and only have one backend that you need to maintain. And at the same time, the client can be maintained only by the vendor, and you don't have to do it yourself if you're the developer of Python, for instance. So the way they do this is using these language neutral protocols, which allows this decoupling between the client and the server. And one of them is this language server protocol, or LSP. And essentially what it does is it has this language agnostic editing support, which takes your actions on some document and translate them into simple text changes. So for instance, it will say on line 4, you put an A, and it will translate this to the server using the protocol, and it will then update its version of the documents and perform this these language actions on the documents themselves. For instance, for syntax highlighting, syntax checking, you could have the server say on line 4, character 3 to 5, you have an error, and this is the error, which the client can then display without knowing anything about the language itself. And the same we have for debuggers. This is then called the debug adapter protocol, which essentially wraps the language-specific debugger in what's called a language or a debug adapter that can then communicate this protocol with some generic UI. So if we look at how you support specification languages, then in normal programming languages, you just have these editor features that are supported by LSP. But for specification languages, you have way more features that you would like to have for your language. And these are not supported by either LSP or DAP, as we can see here by the colored ones. So all the white ones are not covered by these protocols. So currently it's not possible to divide it in a pure client and server part. Some of these features could be theory improving or test automation and all kinds of translation features. So what Frederick and I did was to create this specification language server protocol, which aims to enable this complete decoupling between the client and the server. And it's an extension on the LSP protocol, since the LSP protocol provide a good basis for us to continue on, because it has these 3 basic messages, request, response, and notification. And at the same time, it has a very useful message structure, which allows the use of only some of the features in the protocol without having to implement the full protocol in order to use some of it. It could be that for your language, you only want proof obligation generation and you don't care about combinatorial testing. So you will only implement the proof obligation part. And currently, this protocol is supporting proof obligation generation, combinatorial testing, and translation. the translation is quite simple, so we will need to extend it for more advanced translations, but it's a good basis. And we also have for theorem proving, but it has not been tested with VDM. It's only the 3 top ones that we have implemented. Yeah, so the way we've done this in Visual Studio Code is that we have based it on this language core called VDMJ, which is a Java implementation of the language features for VDM. And we've then wrapped this in a debug adapter for the debug features and a SLSP server for the LSP and SLSP protocol. So because of the nature of this protocol, then in Visual Studio Code, they have these generic modules for both DAP and LSP that we can use and get these features for almost no implementation effort. These 2 sets of features we have written something like 100 lines of code for, and then it provides us the full spectrum of these features. But for our features, the SLSP features, we have created these 3 modules that can be used for proof obligation support, combinatorial testing support, and translation. And again, because of the nature of these protocols, they can be used for any language. They are not VDM specific. Yeah, and then I'll do a short demo of this in Visual Studio Code. So I don't know if you can see this. I hope you can.
Slightly larger.
I can try.
That's perfect.
Yes. So what you see here is just a VDMSL specification, and one of the things that are clear is there's a warning that we get here, and it's from the LSP features that have this syntax and type checking. We also have features like go to definition, where we can jump down here, and we also have some basic auto-completion and some other things from this LSP spectrum of features. But more interestingly, we have the features we have implemented. So one of them is this proof obligation generation that we can right-click and then click here. And it will then provide us, I'll just zoom out a bit again, with this window where all the information comes with from the server, and we then, based on the protocol, know how to display it. And we can see for this proof obligation that belongs to this schedule right here, we need to prove this in order for and we also have some different nice features here in order to make it easier to navigate. Another thing we've implemented is this combinatorial testing, which we have in a specific or a window for that. So if we generate the test downline, then it will go looking for what are there of combinatorial tests in the specification. And we can see here we have these 6 tests, where some of them has been run previously by myself. And if we choose to run these, we can see that the results are coming in as we run them. And it's an advantage that was not seen in the previous IDE Overture. We also have other features that you will also find in Overture, such as filtered execution and what else? Yeah, we can also launch it in a debugger. So for instance, if we have this test, then we can say we would like to run it in the debugger, and if I had some breakpoints that made sense, it would stop there. Yeah, and finally we also have this translation, where if you right-click, you can say, for instance, translate to LaTeX, and it will then generate the LaTeX files up here. Yeah, so in summary, this protocol allows us for a complete decoupling between the client and the server, which is very useful if you want to, for instance, support multiple clients. In this way, we only have one backend that we need to support. Right now, one problem is that we have an implementation in Overture, and we have one that is this VDMJ, and they have more or less the same features, but it's not the same code. And this is one of these long-term implementation efforts advantages that I mentioned here. And also, if we have multiple languages that start to use this protocol, then we can reuse things between the languages. For instance, the client can be reused for our for VDM, but also for a language like PBS. But currently, the protocol has only been tested for VDM, and we can also see here it's still lacking some of the features that we have identified, and there might be some that we have not identified. So in the future, we will look towards using this protocol for other specification languages too. Yeah, thank you. And please let me know if you have any questions.
Thank you, Jonas. Actually, you finished in time, so you would be able to take a single question if anybody wishes to raise a hand. But other than that, my suggestion is people type in the questions in the chat instead. I can also comment that the owner, the writer of VDMJ is in the audience, and there's also PBS people in the audience. Kasper, you have a quick question?
Yes. How much time, say you worked on this on a bachelor's, how much time did it take to implement this on the server side and on your side, on the front end side? If you can give some sort of time estimate.
Yeah, so it was a master's project, but minor correction there. But on the client side, I think it was something like a month to implement all of this. And it's also learning the API of Visual Studio Code and setting up the protocol itself. So if we wanted to do it for another language, it would be way faster.
Thank you.
Thanks for that. And then if you have further questions, I suggest you use the chat. Thomas, could you put on your screen and your camera, please?
Absolutely. Just give me a second, please.
Yeah. Because you may have a Linux issue with sharing things sometimes.
That would be typical. Could you see me? And also my screen?
We see your screen.
Okay.
Please go ahead.
Yes. So, well, thank you for the introduction before, Peter. And as it was mentioned, I will try to condense 3 years into a 20 minutes presentation here. So maybe it will be a little bit loaded, but I will talk about a provable cybersecurity for industrial control systems. So initially, I'll introduce the problematics of security in industrial control systems, complexity, and then touch upon some cybersecurity standards, introduce some formal methods, meaning methods based on mathematics and logic that could help us analyze security for these types of systems, and touch upon some results and compare different methods that were investigated during this PhD study, during my PhD study. So let's hop to the introduction as the very first thing. So one of the things that we need to define first is some basic industrial control system. So we could have some sensors, some actuators that are doing anything, so maybe controlling a production line, and then they are networked, connected to some switch, and we have some engineering terminal where an engineer could interact with this. Well, these were the good old days, at least, where everything was nice and isolated. However, these days, what we would like to achieve is to connect remotely to such an industrial control system, and not only collect data from there, but also provide things such as system updates, firmware updates, things like that. So now this connectivity that usually runs through the internet, of course, introduces some security issues. So how could we analyze and try to build more resilient systems? So in this study, I am investigating use of formal methods, which are some methods that allow us to model the system in a different modeling languages. They are always based sort of on some rigorous formalisms, which means that they are based, or they stem from mathematics. And so we could take some remote terminal unit, some device such as this, and sort of translate it different actions that it can take to something like this. It's called timed automata in a sort of a modeling system called UPAL. And then we could take and try to see, okay, if we have an attack, something like this, that we have here, this is a representation of a distributed denial of service where we try to overwhelm some backend of the system with requests stemming from some front ends. In this case, it's distributed, so there would be multiple front ends or multiple attackers at once. So this is this is some of the basic things. We have a hardware device that runs some software, try to model it, sort of move it into some model-based representation, and then ask questions. Now, security in the industry often follows some cybersecurity standards, and this is what I went into as well. The specific standard that I have considered was this IEC 62443, and the nice one was -3-3 because it provides security requirements that the system needs to adhere to. And one of the things about these standards that they are written in natural language. So this means that sometimes they are a little vague open to interpretation, and they are perhaps not as strict. And one of the things that we would like to do, usually with these kinds of systems, is early in the design stage, sort of try to analyze if our system actually can comply to such a standard. And why do we want to do it early? Well, earlier we do it, cheaper it gets. Don't need to build costly prototypes and all that. As we are working with models, we can easily adjust these. Now, how does something like it look like? Let's say that we would like to formalize a standard, and let's see that we have a system where we would like to crack some credentials. So we have a system that has some login credentials that we want to get in, and attacker decides, okay, I would like to crack this. So this could sort of way of cracking the credential could very naively look something like this. We have some function that checks the credential, and it's either correct or not, so you are allowed access or not. And we can have a recursive function crack that will call this check credential while generating new credential for as long as we have forbidden access. So we're just guessing pretty much, standard brute force attack. Now, within the standard, there is a requirement that has something to say about this, and I'll just summarize this. This is directly taken from the standard, so you could see how big these are. And that is that, okay, we should limit actually the amount of times that somebody could attempt to log in to the system. Now, so how would we do something like that? We need to define, again, a couple of predicates. So we start with something called user account and define a predicate that this user account, for example, can become locked, which means that so we cannot actually be allowed access to the system. Now, we need then, if we should limit this in some way, we should have some attempts, so amount of attempts that somebody tried to log in. And then we actually check that, okay, it's our access, do we have limited access? If yes, then what happens is that our amount of attempts that we have captured here is more than some limit that we set on the system. So here represented as maximum attempt. And this is pretty much sort of written in some nice notation, but it needs to be translated to some automated analysis that we actually want to carry out. So something like that would be translated to, for example, UPAL that is shown here, where we actually try to exceed some amount of attempts for an account and see if this is possible within some specific amount of states or within specific amount of a sort of possibilities that the system runs through. When it comes to the standard, have analyzed about 5 requirements for the standard and some requirement updates as well. Now, this is model checking, where we pretty much built a state space, so check all different states that the system can be in. Usually we can generate all of the states that the system can be in, or we can bound it here where we can say how many states we want to consider for each of the runs. Then there is, of course, more things that need to be considered. How about some cloud connectivity? Now we need to consider remote actors, and sort of this increases the attack surface, and rich features such as collections of data remotely and sort of providing of these updates into the system. So there are some issues that we need to consider. For example, very often we might have some intermittent connectivity depending on what kind of system we are working with, or the systems could reconfigure dynamically, which means that for example, there might be at some point 5 controllers, then all of a sudden it's 6, and they can take different roles upon them. So in case that we want to actually utilize some remote access, we can start again with something like a brute force authorization attacks, right? Where from a remote client, we would like to actually log into the system without having the correct credentials. So in this case, they've considered a client that uses something called client credentials to actually log in, which means it's the client itself considers this, so for example, an application rather than a user that uses this application. And this is one of the float in a protocol called OAuth. However, it also brings some downsides where, for example, since multiple clients can actually share an identity, we cannot simply lock down some offending client. So instead of that, to mitigate such attack, the idea was to provide some location-aware client lockdown. So where we check that we suspend any client whose identity is not valid, and we actually suspend a client, for example, that has attempted to connect too many times from a location which seems to be suspicious. Now, something like this could be again formalized for automated analysis. This is a small snippet of Pascal, which uses an TLC model checker behind and translates to something called TLA+. One of the things why we actually moved from Alloy to Pascal, the idea was let's see if we could use something that is more algorithmic in nature, so a little more imperative style of providing things. But again, we start with something that we say that, okay, we can have some clients that are either trusted or not, and we start with unauthorized without any without the identity being checked, and that the location could either be suspended or not at some point. And of course, then this sort of represents the flow of clients trying to log in, where we actually check, okay, if this location is suspended, then we will not allow this client to actually connect. So again, this is run through a process called model checking that actually generates a lot of all the states that the system can be in, and then we can actually ask some questions about the system. So we, for example, express this as properties. So here, these properties are expressed in something called linear temporal logic, where we could check, for example, that okay, we would like that the invalid IDs always are rejected, and that our locations get suspended if the client is not trusted. So one of the things that is notable with this kind of modeling and asking questions, so these are some of the properties, but all in all, there was more than 20 properties analyzed on a cloud-connected industrial control system. Is that sometimes the time of the analysis could be rather long. So this took over 2 hours when considered the cybersecurity standard. And it could also lead to a problem known as state space explosion, where there is simply generated so many states that they do not fit into a computer memory, and hence the system could not really be analyzed this way. So it is this problem where I attempted different approaches, which was actually, let's split this into different subsystems and use also combination of some statistical model checking, which provides probabilities for different things happening. And if the probability is high enough, then we could run the different modules. So not the whole system at once, but different things. For example, we can take clients and the cloud separately, and the control system separately, and the control system with the cloud separately into these 3 modules from A1 to A3, and can analyze different types of attacks on these things. Of course, one of the downside is that if there is a sort of an attack that flows through the entire system, it's very difficult to split it this way. Now, how does something like this look like? So we would look, for example, into the cloud. Representation of a cloud in this sort of timed automata representation would look something like this. We have different functions that are being called, and then we can wait for some responses from, for example, clients or the control system itself. And one notable thing here is the partial mode. This enables us to then split this into these different modules. So partial mode 1 is one of the modules, partial mode 2 another one, and so on. So we could then in this language also sort of in this system called Buhl create some kind of a representation of different attacks. So for example, this is a representation of the DDoS attack formula that I shown before. And this could be then expressed as a properties of the computational tree logic, where we simply check that, okay, are we overloading the system with requests against some threshold, and also checking if we are receiving enough replies from the system as we would expect given the amount of requests. And you could see that analysis for a distributed denial of service, actually just using that module, A1 already uses 8.2 gigabytes of memory. So this is simply taking 2 clients and the cloud. So it is still quite heavy, even split into modules. Now, another approach is something that has actually been mentioned here already in the previous presentation, and that is to use VDM, where in VDM the system is described a little bit differently, sort of in a sense of this almost contract-based, where we have some invariant pre and post conditions, where invariant is something that needs to universally hold in the system, and pre and post conditions could be defined on different events or functions and operations that happen within this system. So something that we expect that holds before we do something, and something that we expect to hold after we do something. And also, it has been mentioned a little bit about combinatorial testing before. So one of the downsides here is that this system is not exhaustive, so we do not analyze the entire state space. However, using combinatorial testing, we could generate millions of tests simply by adjusting a parameter or two in the implementation. And here consider a couple of attacks. For example, malicious firmware attack, try to upload a malicious firmware to the system, or expired token, where we try to utilize an access token to the system that has been expired. So this would look then something like this. In VDM, for example, this is the representation of the token. And here we, for example, have an invariant that states that our issue time cannot be higher than the expiration time, right? The token needs to be issued before it expires, or there is something wrong with the system. And then we have some operations, for example, performing the login into the system, which will provide us with this type of a token. Now, if we look at the different tools that has been considered and give it a little bit of an industrial perspective, so within the alloy, the very first thing that I have considered for this was that it's lightweight and enables us to set a specific amount of states that we want to consider in our analysis. However, its purely declarative nature was a little bit difficult to sort of take into a standard software development process. Then the TLA plus with TLC model checker, Pascal was a nice language to work with and provided automated translation, easy to sort of understand by software developers. However, the Trace Explorer, where you actually get to see what's wrong with the system, is very difficult to interpret for these tools. And then UPL provides a notion of time, so we could have some time in our models, and provides a simulator, a graphical simulator, where we could see very graphically what is happening in the system. So that's very nice. However, if we need to have discrete timestamps, then this generates a lot of extra states. Finally, VDM and Overture, it's contract-based and very close to software development. However, one of the downsides was that it's not exhaustive. One of the final things that came out of this was a creation of some formally verified components for a industrial control system, a new component that we called Key Vault, and this provides a cryptographic key management for an industrial control system. So, for example, provide the certificates via some PKI solution that are then signed, and this then provides short-lived keys to different controllers that could then be used to communicate themselves in a context of a specific system, meaning that we could guarantee, for example, things such as the controllers are genuinely produced by the manufacturer, and they cannot be just simply taken and put into another system, as they would not recognize that system by a certificate and would require full-on reset, so nothing could be obtained from this controller. So one of the representations, for example, of the certificate, it's like this. It's a typical struct in C, and this has been analyzed using UPL. So this analysis has then taken about 15 minutes of this type of a component. The memory consumption was quite high for an analysis. So we have a lot of certificates and data structures there. So that's plus there is a lot of different states that the system could be in. So consumed around 14 gigabytes. And so this has been then positioned as a basis for a key management system that where we have worked with the help of a few master students on actually implementation of a prototype. And this prototype is now sort of a basis for further analysis and work that we are doing. So there will be more sort of results coming on that. And one of the things that is important to note that this project has shown that indeed formal methods could be utilized industrially to actually analyze existing systems, and definitely can help in development and design of a more secure systems for the future. And with that, I would like to thank you.
Perfect timing, Thomas. Thanks very much for that. I suggest that you stop sharing and we ask additional questions in the other room. And then Morten, if you could share your presentation and turn on your audio as well.
Yes. Do you hear me?
Perfect. Yeah, we hear you and we see you. Thanks.
All right.
Go ahead.
I'll just set my timer.
Yeah.
So, do we have additional for the last presentation, or do we just go on?
No, just go ahead. That's fine.
All right. So I will talk about our project, which a lot of it has to do with doing analysis where the data is actually located. And I've included a picture of a gold digger because that's kind of one of the challenges we're facing with a ton of data in our project and figuring out how we find the right signals and the right indicators in the data. And I think that's the starting point. So the project we're working on is called Bearing Brain, and it has to do with building an intelligent sensor that looks at industrial machines. I'm Morten, and I'm employed at our new joint ECE department as a PhD student and lecturer in Danish. I guess that's an associate or assistant professor teaching embedded systems. I will briefly try to run through what the project is all about and what we have done to try to smarten up our sensor and do the analysis local instead of somewhere where the data is centralized, and some of the challenges we are facing and trying to solve, and a bit about an upcoming or an interesting trend called TinyML, where you run machine learning on tiny devices. So the Bearing Brain project is basically motivated by the fact that when you have unplanned stops, it doesn't have to be in a wind turbine, it could be in your production facility or whatever. It's always inconvenient and quite expensive if you need to stop your production for something that is defective and has to be repaired, and you cannot produce until you're back online again. What we're interested in this project is, in particular, you have probably guessed from the name, is bearings, roller bearings in particular, and whether they are okay or not. Overall, we do that by instrumenting them with various sensors and capture the data in a relatively high resolution and analyze the data and make a prediction on whether the condition is good or not. And the project is running from 2019 till 2023 and is founded or mainly funded by the Danish Innovation Fund. Yeah, this is basically, it's a Danish press release that the Innovation Fund invested about 12 million Danish kroner in it. And we actually did apply for the project twice. The first proposal was rejected, mainly because we forgot to include an end user in this project, and the Danish Innovation Fund likes to see that whatever you're building with their money can be deployed somewhere. So it was originally a collaboration between former ACE, now ECE, and Ceramic Speed, a company that does hybrid bearings. And we thought we could make this killer technology together. And they thought it was a good idea to include the end user. So we included Arla, that had good relations with Ceramic Speed already. They have a live production with a lot of instrumented machines where we can capture data from in a high resolution. Since they just discarded them after initial monitoring or observing the data, we thought it could make sense to capture these data and use ahead in the project. Apart from that, we spent quite a lot of time building experiments and doing accelerated lifetime tests where we are allowed to run bearings till they break, basically, and capture data from that and try to do analysis models. And even though we look quite serious in this picture, it's actually quite fun and have to build both mechanics and electronics and software and stuff and piece it together. So that's a big part of the project. Machine monitoring, as is today, at least performed by Ceramic Speed, that requires the end customer to have each measurement point that could be on a motor, as shown here, instrumented with traditional accelerometers. You have to have data acquisition and cables mounted in your production. In many cases, it would need to be fitted in a stainless watertight box and so on. And that would cost you about 15,000 Danish kroner per measurement point when it's all installed and up and running. Plus, you would need some additional interpretation. Shown on the right is by an elderly man called Henry. That's the expert in the company that does this on an hourly basis. The aim of this project is to build a cheap sensor that you can attach to a machine for around 1,500 Danish kroner. That's a tenth of the existing cost. That runs on batteries and transmits the results wirelessly to some access point that can collect it. Actually, we have wires hanging out in this picture, but our prototype is running wirelessly and communicating over LoRaWAN. And then you should be able to do the remote diagnostics or see the trends or get a notification whenever the sensor detects something and act upon it. Just to run over what a vibration sensor means in the terms we use it, it's basically that you have a sensor that is MEMS, microphone, or accelerometer typically, and you have an analog to digital conversion unit, and you have a microprocessor unit. You sample the data and you capture a lot of raw data. In our case, it's pretty similar to what you would capture in an audio stream, captured at 40 or 50 kilohertz. And you do some analysis on the raw data, and you can do some frequency conversions and spectrograms and so on, and try to do analysis on these data. You could also call that kind of an unintelligent sensor, looking just from the sensor perspective, because you capture a lot of raw data and you need to handle them elsewhere and do the analysis. So obviously, if you have a lot of sensors, in our case at the Arla factory, we have around 80 points that are instrumented, and if you need to capture them at 50 or 100 kilohertz, it would generate a ton of data that you need to store and handle, and so on. Other process parameters that you might typically want to monitor would be temperature, or flow, or pressure, which would be relatively low speed, maximum up to 10 hertz in most cases, where vibration data, if you need to have a good resolution and an early detection of potential failure, you would need to capture it at something like 50 kilohertz or even higher. So what the approach we've taken to kind of smarten up or move some of the analysis onto the device is driven by a couple of technology enablers that makes it possible to do what we're eager to do. One thing is that the availability of cheap and pretty good MEMS sensors, accelerometers, and microphones has, well, the availability has increased quite a bit over the last 5 years or so. Processors are getting cheaper and better at doing more than just sequential processing. They can also do signal processing pretty efficiently on some of these low-cost and low-power ARM devices. Over the last couple of years, quite a lot has happened in the field of being able to do signal processing and machine learning combined on small microcontrollers, quite energy efficient, and that's also one technology that makes this interesting for us. And the last is the availability of low power wide area networking technologies, not only that they are available as kind of a chipset, but also that things like narrowband IoT and LoRaWAN is being deployed nationwide, in Denmark at least, and LoRaWAN you can extend on your own by putting up extra repeaters and so on. So that's kind of the enabling technologies that we've pieced together to build a solution, which means that you could take your unintelligent sensor that was presented before, and by doing the data capture as in a traditional fashion and adding the ability to think and transmit on top, we could call this TinyML in this case, we could do most of the processing on device and just send the result instead. And if we only have to send the result opposed to raw data, we would need much less bandwidth on our wireless radio communication, and that allows us to stretch the battery life quite significantly compared to having, for instance, a Wi-Fi or a Bluetooth connection that needs to stream raw data. Right now, we've built a first prototype that you see on the right here. It's not that big. It's actually bigger on my screen than it is in real life, but it's relatively small, and it takes an AA battery, and it has a couple of accelerometers and a microphone and temperature sensor on board, and a nice mechanical enclosure so we can start testing it on machines. And it has a Cortex M4F microprocessor on board, and this processor can do a few interesting things. It has floating point extension, and it can do what's known as SIMD. It can do multiple instructions at once, and if you run 8-bit instructions instead of 32-bit instructions, you can do it quite efficiently in terms of doing analysis and things like that. So a few of the challenges we are working with in the project, I'll just briefly introduce them. One is the fact that when you have a defect coming up in a machine, if you wait long enough, you can easily detect it because you can just stand next to the machine. You can either feel it vibrating or hear it, or you can perhaps smell the smoke. So that's on the right. The earlier you want to detect it, the faster you typically you have to sample your data, and the more sensitive a sensing device you have to install. So acoustic emission and ultrasound, some of the early signs of a bearing damage coming up. And we're looking a bit into, in particular, ultrasound microphones. And then when kind of the damage progresses, you would start to see vibration that you can pick up with a good accelerometer. And as the damage worsens, you can easier capture the damages with a low-cost accelerometer and so on. But the longer to the left you want to be, the better your sensor has to be, or the more sensitive and the more high-frequency sampling you have to do in your sensor. So that's a trade-off between the higher you want to sample, the more energy you consume, and the lower your battery lifetime would be. Also, when we need to train machine learning models and analysis models, we'd like to start out with some available data because it takes time to capture data from machines on our own. And since most data available on the internet is focused on video or audio and a lot about cats, actually quite a few on vibration from industrial machines, quite a few. There's not that many on industrial machines. There are some accelerometer data. Some of them are about human recognition, but there's a handful of good data sets that can be used, but not quite as many as if you were looking into image classification or audio classification or whatever it may be. So we're collecting our own data from these 80 data points instrumented in machines at the Arla factory. Wireless transmission is also a challenge. Here's a plot of, it's called the path loss exponent. You use it when you calculate link budgets, and there's some numbers that might be hard to see, but what it basically tells us is that the more obstructed we have, the more obstructions we might have in our signal path, the more the energy consumption to deliver something from A to B goes up, and it increases exponentially, unfortunately. And the environment that we're working in, you can see it here, it's very crowded with steel pipes and steel everything. So we have quite a challenge in terms of radio propagation in this environment. So in our case, we're currently using LoRaWAN and looking at narrowband IoT because they are some of the technologies well suited for this kind of tough environment. I'll just jump briefly over the last couple of slides here. So Wi-Fi is actually not an option for us because on a typical Wi-Fi microcontroller, you could use between 300 and 800 milliwatts of power, and you need a giant battery if you need to run that and wake up and get an IP and so on. So that kind of disqualifies itself, and we've looked towards these LPWAN technologies instead. Also, the fact that if you have two identical machines, they look alike, at least you can have a very different mechanical transfer function from the bearing out to the sensor, and that also gives some challenges in terms of how you tune your analysis model to figure that out, even though the machines should be identical. Before I round off, I'd just like to introduce this upcoming trend, I would say, that called tiny machine learning. The fact that you can run optimized machine learning models on small microcontrollers. It's a mix of kind of getting the best from certain microcontroller architectures and having optimized software libraries and having some algorithms that are suited for compression and quantization, but it's something we're looking quite a bit into, combined with signal processing. That basically means we can run it off a small battery instead of a giant battery on our sensing device. You can do stuff like keywords and audio classification, which is what we're looking at on a small microcontroller like a Cortex M4 device or even smaller, and that's interesting from an energy perspective when you need to live off a battery for more than a year, and you can't have too much service on a sensor like we're building, because then it would cost more time than it would actually save the repair crew. And I have 5 seconds left, so I won't get much into detail, but basically what this is supposed to show is that if you do 8-bit calculations instead of 32-bit calculations. And if you do, if you keep your stuff in internal memory on a microcontroller, you can do it with much less energy cost than if you need to run it on, let's say, a Raspberry Pi where you have external DRAM and so on. That's what's also setting limits, but also an option in terms of building very small models. Calculating example is that you can run image recognition in 110 microjoules. Actually, if you have an optimized model, that means 110 microwatts if you run inference once per second, and that can have your device living for a long time on a battery. And so I think my time is up.
Wonderful. Thanks very much, Morten. And again, questions in the chat, please.
Yeah.
Now we'll change gears and move away from the hardware side into how can we do simulations and co-simulations and design space exploration. So Max, can you try to share your screen and your camera?
Yeah. That one? That one, I think?
Yeah. We see your screen and you see it in presentation mode, so go ahead.
Good. Hi. I've been looking at sort of extending the design space exploration options in the INTO-CPS toolchain with genetic algorithms and also some other improvements to the design space exploration scripts. This has been my undergraduate dissertation. Here is my email, and also my supervisor's is also on there. So we're going to start with the other improvements first. Probably the most noticeable improvement for a lot of you that use it will be we've now upgraded to using Python 3 instead of Python 2. Obviously, Python 2 has now been deprecated for a year and a half now-ish. So it's going to be a lot easier, especially for a new user. They're not going to have to downgrade their Python version anymore. We've also implemented threading so we can run multiple simulations at the same time. As we can see here, from the measured and theoretical time to run an entire DSE, it performs pretty much close to the theoretical values that were measured when using around 100 simulations. So this means we can do more DSE in a lower amount of time. We've also added some more options to all the DSE scripts, including what I've done with the genetic algorithm side. So obviously, we've now got a new option for thread counts. Previously, the old scripts would generate both a CSV file and a HTML file to display the results of the DSE. Now, both of these are optional in case you just wanted to process the data on your own. We've also added an option for the co-simulation engine to be put as an external resource, as it runs as a server anyway. So we can pass it a URL with a port in case, for example, the simulation engine was running on a central server instead of your local machine. So we'll just go a little bit over what are genetic algorithms. So a genetic algorithm is a system of functions that was developed in around the 70s to mimic the process of natural selection found in nature. Due to the system being based on nature, it is incredibly flexible and so highly suited for a toolchain like INTO-CPS, which is dealing with highly diverse cyber-physical systems. With the simulation, with the system being based on natural processes, the stages of the algorithm are pretty much matching what's found in nature. So selection will rank the organisms based on how suitable they are for your specific scenario. Then these rankings are taken into the mating stage. Mating pairs organisms or combinations of parameters based on their fitness, or generated in the selection phase. This is to mimic nature, where the most suitable organisms are more likely to produce offspring. The crossover stage is where we actually create the children of the organisms, which are based on the two parent organisms. Mutation will then take those offspring and alter the values slightly so that the diversity of the system is maintained, so we can more quickly get to the solution we want. Finally, the elimination stage will take a percentage of the previous generation and add it into the next generation to be run. This is so we don't lose the best organism, basically. So it'll take maybe the top 2 or 3% found from the selection process, as mutation can inadvertently remove potentially the best solution found. And then if we're satisfied with the combinations that we found, we can then finish and print the results. And obviously, if you wish to simulate asexual reproduction, you can simply remove the mating stage there and the crossover stage. So what's the point in using GAs for DSE? So prior to this, the real only DSE options available in INTO-CPS were an exhaustive search. And whilst exhaustive search is a good option, it may not produce the best results, as it's limited to the values that are initially given to it. Thus, if no combination of those parameters are actually optimal, then it won't find an optimal combination. On the other hand, a GA-based system isn't limited to the values it was initially provided with, meaning it can potentially have a higher probability of finding an optimal combination. A GA can also be beneficial if you would like to maybe explore a system that you've already explored with an exhaustive search, to see if there's maybe a little bit more performance you could get out of it. Or if you just simply don't know any kind of parameters that you that you could start with. So it's a great way to maybe start an exploration into a system. A limitation of a GA-based system, however, is that it's not guaranteed to find the absolute best solution. For example, if a search space has a lot of locally good best solutions, then the system might get stuck in one of those and not find the solution that is optimal globally over the search space. The GA is also content with finding a good enough solution is as close to the best solution as you define, but the good enough solution may not be the absolute perfect solution. So with the implementation into INTO-CPS, it's all in a GitHub repo, just if at that link. So we're using the standard JSON configuration that's been used for the exhaustive searches previously. And there's also functionality where the system that I've implemented is completely modular. So if you want, you can completely disable parts of it. You don't have to use all of it. And also, if the functions that I provided aren't quite good enough for your specific needs, you can easily implement your own and configure them in the JSON file, and it will know to find them and use them. So if we look at an example configuration, it looks very similar to the normal exhaustive search. Simply we need to specify that we're using a JEC algorithm. The parameter constraints are carried over from the exhaustive search side, where after the crossover stage and the mutation stage, it will run these parameter constraints. If the algorithm doesn't fit them, it will make it fit them. The parameters are where the starting search space. So the initial generation will be generated from whatever range is specified here. And then in the genetic argument section, this is where we specify the arguments we want to run our genetic algorithm system with. All of these are explained in the GitHub repo as well for more information. So to test this, we used 4 different test functions chosen for their different search spaces. This was to ensure that the system was robust enough to handle the diverse search spaces that can be given to it with a cyber-physical system. The test functions given were a simple x² function, a sphere function, a Rosenbrock, and a Rajastragan function. x² was chosen as it's a simple one-dimensional function that was being maximized from 0 to between 0 and 32. Just to make sure that the system actually worked. The sphere function, which was chosen as it's possibly the next simplest after x². It has a single minima, and we were minimizing the other 3 between -2 with a parameters of -2 and 2. The sphere function was chosen as it's got a very simple plot here, as we can see here, with a single minima at 0, 0. The next function was the Rosenbrock function, which was chosen as, whilst the valley is easy to find, the actual true minimum of that valley isn't that easy to find. So it was a good test for sort of places where an optimal solution is, but maybe is hard to find. And finally, the Rajastragan function was a good test for a function with a lot of local minima, so we can ensure that the system has methods of not getting stuck in a local minima. To test the system, the 4 functions were implemented as a simple VDM controller with 100 generations and 100 organisms in each of the generations. For the x² functions, these line graphs on the x-axis is the generation number, and in the y-axis is the function results. In the x² function, the best value we found was 1023.978, and with a deviation of 163.326, which means that the diversity of the system hasn't been utterly destroyed. So if the function did have a lot of local minima, the system would have been able to escape them. And the best value of this, of course, being 1024, 1023.9 is pretty close. Next, the sphere function, which this graph doesn't have as much diversity, but we still found the minima at 0, 0, or very close to 0, 0 at 9 times 10 to the -35, which is close enough to 0, I would say. Next, the Rosenbrock function. Again, this took, if we look here, this found the minima at around just before generation 10. The Rosenbrock function found it just slightly after generation 10. So we can see it is harder. It was harder for the system to find this solution, but we see it did find a solution at 0.298, which we were minimizing to 0, which again, they're very good. And finally, the Rajastragan function, which, as we can see, it took a lot longer for it to converge again. But we did find a best value of 0, so we've done very well there. So from these results, we can see that the GA system is performing well under many different test conditions, and that we can move on to a real case study for a more realistic test of the system. Case study, we looked at the Robotti, which is an autonomous farming robot produced by AgroIntelli. And it was based on the work done by some lecturers at Newcastle University for the controllers and all of that. And the goal of this was to replicate the results they found. So in doing so, running the Robotti through the controller, we can see that the GA did find something either very similar or exactly the same as the exhaustive search, which means that, again, the system is very good and a good option if you want to do something other than exhaustive search. The slight difference in cross-track errors here is because the values in these tables are rounded to a more sensible value. And I have 10 seconds left, so I think I'll end it here. Thank you for listening. If you, my email and my supervisor's email is here, and if you would like to see the full write-up, you can find it at that link there. Thank you.
Thanks very much, Max. Maybe you could type in the link into the chat afterwards.
Yeah, we'll do.
This leads perfectly up to the next presentation, which is also related to Robotti, but a desktop version of Robotti. So, Gill, will you share your screen and audio?
Yes. So, can you see and hear everything all right?
Yes, perfectly.
Okay.
Go ahead.
Great. Yeah, so my name is Gill, and this presentation is about some work we did for our bachelor project during the fall of last year. Did this together with Jakob Hausted and Jakob Levisen. And yeah, it's about some work towards digital twin systems for autonomous robots, and more specifically, it's about the goal was to combine robot functionality that's been implemented using the robot operating system, to combine this with the existing co-simulation tools in the INTO-CPS toolchain, and then to demonstrate different types of behaviors and interactions between the physical and digital systems. So our work focuses on the desktop Robotti case study, and you heard briefly about the Robotti before. The desktop Robotti can be seen here to the left. It's a desktop-sized version of the big agricultural robot that's made to automate different farming activities. And then the purpose of the desktop-sized version is to of course mimic the behavior of the real-sized robot, and then to provide a lightweight platform for experimenting with digital twin functionalities that involve this type of physical system. Yeah, so here you can see the desktop Robotti in action. I think I can only start the video if my laser pointer's off. 2 seconds. Yes, and as you can see, the robot behaves as a car in terms of steering and speed control, and then the robot is equipped with a Raspberry Pi as the primary onboard CPU, which is connected to a Wi-Fi network, and then it's also equipped with a 2D LiDAR on top for scanning the environment. And so, yeah, the purpose of our work was to create a kind of a testbed for experimenting with digital twin scenarios, and to iterate on the hardware and the software for the desktop Robotti in this context. So the initial focus was on implementing some example functionalities to test the infrastructure in different ways. More concretely, we focused on simulating the movement of the robot, and to provide some means to evaluate the similarity between the simulated movement and the actual movement of the robot. And secondly, we wanted to support decision making on the co-simulation level, so to allow the co-simulation to affect the operation of the physical asset based on evaluation of sensor data. And then lastly, we wanted to visualize the system operation in 3D. Yeah, so as indicated before, we use the INTO-CPS toolchain for all the co-simulation activities. Just a brief overview. I think most of you probably already know this stuff, but yeah, a co-simulation is basically a joint simulation of multiple subsystems that are running in parallel. And then we use the functional mockup interface to specify these simulation units that are also called FMUs. And then there's a variety of tools to generate these FMUs. For our work, we've used a tool called UniFMU to implement some of these FMUs in Python in order to interface with the Rust2 client library, which makes it possible to interact with the physical system, which uses the robot operating system to manage all the functionalities. And yeah, so here's a high-level overview of the system that we've implemented for this project. And as you can see, there's some general functionality like the infrastructure itself and co-simulation visualization that isn't specific to any one use case. And then interfacing with that, we have the Desktop Robotti software. In the center of this system, we have a virtual machine that's running Ubuntu. And this hosts all the co-simulation activities and the user interfaces along with the different visualization tools. And then we have visualization for that's native to the RUS environment, and then we have a custom-made co-simulation visualization that's made to visualize the contents of the co-simulation. And yeah, this virtual machine is connected to the Wi-Fi in order to communicate with the robot. To the Rust2 network. So here you can see all the specific components that are part of the example system that we've set up for executing a few different proof of concept scenarios. In the left side, we have all the components that are running inside the Rust2 network, either on the Raspberry Pi or on the virtual machine. And this includes some components for motor control, for regulating the steering and speed of the robot in response to movement commands. And these movement commands is, in our case, sent from a teleoperation module that's running on the virtual machine. Then there's some nodes related to collecting and processing data from the 2D lidar and detects obstacles in the environment. And there's also a localization mechanism, and for this version of the system, the localization is also based on environment data. Yeah, and on the right side here, we have the components that are related to co-simulation, and this includes some FMUs that model the robot's response to movement commands and tries to estimate a pose based on that. It's divided into two components. First, we have the actuation model, and the actuation model encapsulates the response of the motors and the response of the low-level speed regulation in order to model the adjustment behavior of the robot when new movement parameters are received, and then the estimated speed and angle are then fed to a kinematic bicycle model, which estimates the corresponding change in position. In addition to that, we have a safety monitoring FMU, which is a simple implementation that evaluates incoming sensor data from the physical system, and then has the ability to send back an emergency stop command if it identifies a potential safety issue. We've also implemented a configurable visualization tool for the co-simulation, which generates a 3D environment based on the state of the simulation units. And since we have information about the physical system as well inside the co-simulation, we can visualize data from both the physical and the digital system at the same time. And then lastly, there's a communication bridge between the two parts that translates messages from the Rust network and the co-simulation environment. Yeah, so a bit more about the co-simulation visualization. It's this is a proof of concept implementation that's made using 3JS. And the goal here was to implement a flexible way of visualizing co-simulation results that is compatible with the existing INTO-CPS tools. And the idea is to allow the user to define a selection of objects to represent the different system parts, and then specify how the outputs of the FMUs should manipulate these objects through a series of bindings. And so this is an example where a 3D environment has been configured to contain a ground floor and then two triangles or cones. And then the position and orientation of the triangles can be bound to the output of certain FMUs to visualize a pose, and then update the state based on a simulation step. Okay. Yeah, so just to recap, the goal was to create the foundation of a digital twin framework, so that a user would be able to evaluate the similarity between real and digital movement, and then secondly, to allow for a safety monitor to within the co-simulation to halt the operation of the robot, and then lastly visualize the operation in 3D. And to test these functionalities, we've defined two test scenarios to validate the systems, and these are the parallel operation scenario and a co-simulation safety monitoring scenario. First, the parallel operation scenario involves sending the same movement commands to both the physical and the digital system, and then in real time, and then use the results to visualize the behavior of both twins in 3D, and then also do some manual analysis of the data. And for the parallel operation scenario, we use most of the components in the system as shown here. So basically the movement commands and the measured pose are sent from the physical system to the co-simulation, and inside the co-simulation we then use the same movement commands to simulate the movement independently of the measured pose, and then it's fed to the co-simulation visualization in the end. And here we have a co-simulation visualization that's configured as I shown before, with the two triangles to represent the robot movement. And then we did a 30-second test where we instructed both robots to perform a 3-point turn. And then we can see that they seem to be correlated, but they slowly drift apart over time, as could be expected. Since there's no feedback mechanism. So here we have the results of this experiment, and we can see the two trajectories here on the right, and on the left we can see that the error, which is the red line here, the positional error between the two, it increases over time, and there are certain points where the deviation gets amplified, for instance, here in the end, when the robot is slowing down. And then future work would be aimed at minimizing this drift between the physical and digital robots. So the second scenario is a co-simulation safety monitoring scenario where the robot operation can be halted as a result of a safety distance to an object being violated and monitored by a safety monitor within the co-simulation, and this is to test the bidirectional communication between the physical and digital systems. And yeah, for this scenario we've deployed the entire physical system and then the safety monitor on the co-simulation side to receive current data about the system and send an emergency stop back if it identifies an issue. And so here you can see the experiment where we have a virtual obstacle in front of the robot, and then we instruct the robot to drive towards the obstacle, and then when it gets too close, the safety monitor raises a flag and sends an emergency stop back to the robot, and after that the robot can't be operated anymore. And so here are the results from this experiment. We can see the trajectory of the robot and the safety distance here on the right. And then on the left here we can see the data from the safety monitor that it uses. And an interesting thing to note here is that there's a significant end-to-end delay between the decision to halt the operation of the robot and the robot actually stopping. So this is a place where there's clear room for optimization as well. Yeah, so the bidirectional communication works, but there's still a lot of work to be done on this. And yeah, so in conclusion, we've implemented some first steps towards a digital twin framework for autonomous robots, and we were able to demonstrate the robot operating system and the INTO-CPS toolchain working together to execute some proof of concept scenarios involving movement simulation and safety evaluation. But there's, of course, a lot of room to expand and optimize on the things presented here, and some of the things we are currently working on or count on working on in the future. That involves increasing the alignment between the physical and digital twin, of course, through various means, and then also introduce some feedback or synchronization mechanism into the Desktop Robotti, into the digital twin setup. Other than that, we're working on integrating the 3D visualization directly into the INTO-CPS application itself, and currently we're also developing a new and upgraded version of the Desktop Robotti, and we hope to in the future perform some scenarios that involve multiple robots working together. Yeah, I think that was all I had. Feel free to contact.
Thank you. So if you stop sharing, then I'd like to give the floor to Lasse and Daniel for something completely different. If you, I don't know who will be sharing.
Peter. I'll be sharing. Can you hear me now?
Yeah, we hear you perfectly. Yes.
Okay, cool. Let's see if this works.
Can you hear me as well?
Yeah, we hear you as well. And questions?
You should be able to see.
Yeah, that's perfect.
Yeah.
Okay.
Go ahead.
Yeah, so this will be a brief presentation of our thesis project that we conducted this last semester. Our project was called Biologically Inspired Multimodal Fusion Learning for Robotic Object Recognition. And I'm Daniel, and
I'm Lasse.
Yeah, and yeah, we'll go through our project now. So we will briefly go through an introduction of the problem that we try to solve, and then we will explain the data sources and the data collection phase in the project. Then we'll go through the classical approach to this multimodal object recognition, and then briefly explain the biological inspirations that we used instead to try build a different version of a model for object recognition, and present the results of that. So the problem today in object recognition, we have visual object recognition, which is a very mature technology where we can recognize a lot of objects. However, there's the problem of ambiguity, where as you know, it's very, you cannot see if an unclear container is empty or full, and other more complex scenarios occur where ambiguity is introduced both in the visual modality and also in other modalities. So we try to take inspiration from the best machine that we know to fuse data from different senses. It's the human brain, and try to see how does the brain conduct this problem of identifying objects, not only from vision, but also from the sense of touch using haptics. Yeah. Yeah,
and to actually solve an object recognition task, we need some data. And unluckily, the data space or the data sets in visual haptics are quite sparse, at least for the grand detail that we wanted to use. So we ended up deciding to record our own. So we collected 65 objects approximately of different sizes, colors, materials, and so on, in order to represent a broad spectrum of different objects. And to fully or to be able to mimic this this combination of different inputs that happens in the brain, we needed both visual and haptic inputs. And we split the haptics up into two modalities, you can see on the right here. And I'll just walk you through briefly what each modality contains. So the visual is pretty straightforward. We used 3 images from 3 unique angles, and we tried to keep the setting for the images as good as possible, in order to not give the visual input an artificial disadvantage when competing with the haptic input. Because we already know, as Daniel mentioned, recognizing objects using images is a pretty well solved problem. So we wanted to prove, or to be able to conclude something about the benefit of using haptics as well. And we did this by constant distance, wide background, good lighting, high-res camera, and stuff like that. So the next one is the kinesthetic modality, and both of the haptic modalities, this one I'm talking about right now and the next I'll get to, were inspired by a researcher from the 70s exploring how humans explore objects. So there's a list of human exploratory procedures that we try to mimic in our robots. So for kinesthetic, we used exploration using a robotic hand that is holding the object, enclosing the fingers around the object, and we then measure the position of each finger in order to get a sense of the shape, but also the size of the object. We then increase the pressure in order to measure the hardness, and by measuring the current in the wrist joint of the robotic hand, we can actually see how much it weighs as well. So that's the kinesthetic. And for the tactile, we used a Now robot, which is a humanoid robot. I'll show you an image in a minute, combined with contact microphones and a 3D printed thimble in order to measure the vibrations created by the interaction between the robot and the object. And here we used the exploratory procedures for poke and for feel, where poke leads to information about hardness and feel leads to information about texture. So that's poking and kind of strafing the object. And here's just an overview of our experimental setup, at least one of them, where we have the Now on the left and the robotic hand on the right holding the object. And we then programmed the Now robot to execute the sequence, and we measured the vibrations through these contact microphones that are mounted both under the object on the robotic hand and also on the Now on the right hand side. Yes.
Yeah. So now we have collected this data set of multiple modalities, and alongside with our project, another project was conducted when where the classic approach to multimodal object recognition was used. In the classical approach, you have these modalities that are fused in some manner. So you have the visual modalities, which are simply some images. And then you have the kinesthetic and the tactile modalities, which can be fused into this haptic modality, much like the sense of touch in humans. And then you can then fuse these two modalities into a single modality, in which can be classified upon. Alongside with these fusions, some feature extractions can also occur in order to get some data in sizes and dimensions that are able to work with. For our project, however, we used an inspiration from the brain, where we also have the vision from the eye, and then we have the haptics from the tactile and kinesthetic measurements, as Lasse explained. In the brain, however, there's a lot of things going on, but we chose to focus on two principles that we identified, which is the principle of hierarchical processing in the visual cortex. And the principle of hierarchical processing is simply that when the eye sees something, it goes to the visual cortex in the back of your head, and it conducts a level of feature extraction, much like what happens in CNNs, building some high-level features. And alongside with the visual activations, we also see haptic activations when conducting MRI scans of blind people and people closing their eyes while touching objects. So there's in this visual cortex, we see some kind of fusion between the visual and the haptic modalities, building some kind of features. The secondary principle that we identified was the principle of parallel processing. So when you have built these high-level features in the visual cortex, there's also MRI scans identifying that along the ventral pathway going on the side of your head to above your left ear, there's happens a further high-level processing where you see activations dependent on the object material or the object shape. And these activations happen in parallel, but in different areas of the brain. So at some point, there's a split in the information giving these two different properties. And from this point, there's currently no knowledge in the brain on how you actually go to a classification saying, okay, now I know this is a square rubber cube. So we also had to find some kind of mechanism to fuse these two properties into a single object classification. Yeah, so this was the biological inspiration we used in this project.
Yeah, and from this, a part of our project was to kind of map this to a machine learning context, because we wanted to be able to train a model to recognize objects using principles from the brain. And what I'm going to walk you through now is kind of like our base model. So this is our model that is core for all of our experiments, but we won't get into specific architectures of the model that we mention later. So just know that it's all based on this model. So we start with the same three modalities that we had all the way through, and we then constructed these 6 intermediate abstract understandings of objects. And that sounds very fancy, but what it is basically just what Daniel already mentioned. That happens in the brain in hierarchical processing, where we combine information from different modalities to get some. In our project, we call them property descriptive features. So not quite raw features, but not quite these shape and material properties yet. So these we identified 6 different property descriptive features, both limited by what we could extract from images and collect using microphones, but also inspired by what we see in the literature that happens in the brain. And the 6 of them are shape, texture, size, weight, color, and hardness. And each of these 3 modalities on the left lead into one or more of these property descriptive features. So from visual images, we can extract shape, texture, size, and color. From kinesthetics, we can extract shape, size, weight, and hardness. And from tactile, we can get information about texture and hardness. Yeah, so this is our mimicking of how the brain does the hierarchical processing, breaking down raw data inputs into abstract understandings of the object. So then the next principle that we want to mimic was the parallel processing. So what we do specifically is we feed the shape into a shape property, and we then fuse the rest of the property descriptive features into this material property. We then fuse these 2 again and use the output of that fusion as input to our machine learning model. So the things that we varied were, for example, our methods for fusing, where we used symbol concatenation or slice concatenation vectors, and of course gave different results. We also used some kind of weighting mechanism, more specifically self-attention, to try to see if weighting the output of the fusion would help. And we then varied whether or not we had the parallel processing as part of the model and stuff like that. Okay.
Yeah. So now we have the different principles that we build upon, and we then set up a different variation of models, as Lasse just mentioned, in order to test the principles that we have found. And we simply see that from these single modalities that we have built, we could extract these features, and when we fuse these features together in the single modality, we see that we have these performances over here where the visual input is best as expected. However, when we fuse the data together, the features together, we see a significant performance increase into 96.8% using hierarchical processing. When we also apply the principle of parallel processing, we don't really see a performance increase. So yeah, we definitely see a potential in the hierarchical processing, but not in the parallel processing. Yeah.
Yeah, and in addition to that, we see a great increase in performance using slice concatenation vectors over sim concatenation. And on the other hand, we didn't see any increase in performance using this self-attention weighting mechanism. So the next question we want to answer is, can object recognition systems benefit from adopting this brain-inspired processing? That's kind of what we build our whole thesis around. And Daniel already partially mentioned that where we split the inspiration from the brain up into two principles, where we conclude that the hierarchical processing definitely does something, but we can't prove that the parallel processing actually increases the performance. But to actually answer this question, we have to once again bring up our colleague Christensen, which did a simultaneous project with us and did on all the same data and with similar feature extraction methods, but simply just processed the modalities separately. And his highest performing model was 92.6%, where, as Daniel already mentioned, we had a 96.8%. So roughly 4 percentage points increase by using this brain-inspired processing. That's it for our presentation.
Fascinating. Thank you very much, Lasse and Daniel. If you stop sharing, we'll have Kristoffer giving the last talk here. And questions, of course, can be raised in the chat thing in there. So, Kristoffer, can you share your screen as well?
You should be able to see my screen
now.
now.
See your screen now, perfectly. Go ahead.
And you can all hear me, I guess.
Yeah, we can. Perfect.
Good. And like this, great. So my name is Kristoffer. I've worked together with Hugo over the last period of time here when I've been at Aarhus University, where I've worked with improving and helping with the INTO-CPS application with regards to all the awesome and fun stuff that the open source people and people from the university come up with us and sort of to improve this tool to be used for everybody here. So yeah, it's with me and Hugo, and I will put up my contact information, and I hope Hugo will do the same in the chat so people can find us if need be. So this talk here, for those of you who's wondering, this is not a too technical presentation. So use the next 8-9 minutes to sort of rewind and absorb all the awesome things that you've heard, all the technical things you've heard. Now it's a bit more relaxed, where we just go over some of the fun things that's happened in the tool. So we've talked a bit about the INTO-CPS application, but it's basically what we've talked about is this collection of tools where we can develop and aid into the development of cyber-physical systems, where we are basing this on the formal fundamentals of different parts, sort of the VDM models that we can make. And these functional mockups that we can make, and with an interface standard, we can be able to use these functional mockup units, or FMUs, to create models and co-models of different physical and cyber-physical systems, and then use this in co-simulation to sort of create different models and look into how can we use DSCs to sort of explore the possibilities for our models. And one of the stables that we've used is this line following robot, where we will look at the relationship between sensors and motors on this cyber-physical system, where we can sort of tweak different things and see how do the model perform best given the in the bottom right corner of the application. You can see the line that the robot is following. Should this be precise, or should we cut some corners and stuff like this? Is what we sort of can optimize in this given model here. And then sort of what the app is, as we talked about, these collections of tools are what we see on the right far left here. These third-party tools, the science-based exploration tools that we are collecting from Git, the maestros and the engines that we use to sort of create these, run these models. It's all put together in a Node.js setup where we have on top of that TypeScript and Angular, which is all packed together for a desktop application using the Electron framework to create sort of an INTO-CPS desktop application. So this is the very basics of the INTO-CPS app. So we have that in this understanding. But what does that give us? Well, that gives us this application here. This is the almost the current version we have. We have a slightly newer model out now, where we're able to, based on these configurations in our models, we are able to create simulations of how these robots or different code simulations should run, and we see an output based on the simulations for the different models. And here we can see the line following robot, and it's just to give a sort of an understanding of what can this tool give us in a sense of both a mapping of the relations, but also sort of an image of what's going on. And if I continue, so what has then happened for us over the past year and so, and even a bit more, what we have been working on for this spring here mostly has been to optimize both the UI improvements, but also to give the user experience a lot more choices and give them a lot more to work with. And one of the things we've done is create the results from these different analyses that we do. So you can see on the right here, we have the different analyses from running the robot, and this sort of gave us the Pareto points for some analysis that we might have made. And having that directly in the application is an ease for the users of the application. This is one of the things that we're very happy that we've gotten in here. Another thing is that we've by upgrading the support frameworks, sort of the Angular frameworks and the Electron frameworks, has given us the ability to use newer technologies. One of the things that we've added is the installer to our application. This gives us a much easier way of packing the tool, and a much easier way of installing the tool in the user end. This means that the user will have a much smaller application and a much faster installation and a much cleaner installation of the tool. We've also, as a whole, as a what we call as a team, we've created sort of an approach to how do we develop and how to release steadily process or products over the past year. We can see that at the start of 2020 we got into a process with a lot of heavy development, but we've sort of flattened it out to have regular development and releases in a way that makes it possible for us to have a steady curve of development and helping out the users of the system. As we see, we've closed over almost 30 different issues from people all over who's using the tool. And then we have created a great new community, and we have started out with having discussions on our Git repository to bring in people who are interested in having a chat with us and giving back to the project so that we can continue to deliver exciting new things. And then we have done a lot of size optimization for the application as well, which I'll come back to a bit later. So besides this, we've increased the DSE view, and then a lot of praise should go to Max, as we heard earlier, with his threats and his optimization of the DSE, and very many thank yous for upgrading and helping us with Python, because getting out of Python 2 and into Python 3 helped us a lot and removed a lot of headaches for us. So you can see the new DSE view, where we have the ability to tweak the number of threads and what comes out of the different operations. Again, helping the user with a better understanding and a better feel of what's going on and what are the options as a user in using this application. And we talked about the release process, and one of the things that really helped us here is also the automated tests that we have set up, and that's running when we can do this work, such that we can create a new version, start the release process, see that everything works, that we're not doing changes that has a poor effect on the performance or the tool of itself. And then with all these new all the new changes we've made, we have changed it such that the installation time or from the download of the application and until you can run it on your computer has gone from 6 minutes down to about 30 seconds on a standard issue computer. And the size of the application has moved from around 700 megabytes down to about 90 megabytes. So all in all, we are quite happy with where we are at for the size and for the installation time. And this should be said that this is without removing any features that has effect on developing or using the tool. This is purely optimization of how and what we are doing. So what are we and who are we? We are a community of enthusiasts that are very happy to develop and work together. And as you can see, we have a lot of fun meetings where we all smile, and it's not set up. As you can see, we go to bars, even though that we are in a Corona lockdown. But it's not just all fun. We of course are very interested in having a good workflow in our system. And then just lastly, what are coming into the INTO-CPS application, and what do we want for the future? Gill already talked a bit about this, about the 3D rendering that we want in the INTO-CPS application to sort of again improve the user's experience and give a better, more complete solution. Then we have work with Newcastle. Besides what Max already did, we want to improve even more with the console outputs, where we want to improve the readability of them. And we want to improve even further on our test optimization, such that even smaller tests can be automated in that sense. And just as I've talked a bit about, if you have throughout these talks today have heard anything that you think this would be great to have sort of in the cyber physical environment, and I could see that being possible to be created, but I don't know how or who I should talk to, then going to the INTO-CPS application and go to the discussions and start a discussion with me and the colleagues or other enthusiasts about how can we improve, then you're welcome to do that. And in the link, you can just follow that there, and then we can discuss all the fun things that can be done for the INTO-CPS application. That's all for me.
Wonderful. Thanks very much, Kristoffer. So now I'll just do a quick wrap up. I have one slide to share with you, and essentially that's for the future events. We have the dates announced, and in case you would like to present at the future events, you can just register that. You can also alternatively just send an email to me on that, and you can also email Lita with respect to these future events in case you don't like doing it online. But other than that, I'd like to thank all our speakers and all of you for being present here. Have a nice day. Bye, everyone.